Hello, everyone. Thanks for joining us today. This event is brought to you by Data Talks Club, which is a community of people who love data, and we have weekly events. Today is one of such events. So on Tuesdays, we have webinars, and on Fridays, we have podcasts. So there is a link in the description. You can click on this and find out more about all our amazing events. And then if you haven't subscribed yet, click on this big red button, because if you do this, you'll get subscribed to our channel and you will get notified about all the amazing content we will publish. And finally, if you haven't joined our Slack, do it now, because that's amazing. You'll be able to take part in great discussions about different data topics. During today's presentation, you can ask any question you want. So there is a link pinned in the live chat. So just click on this link and ask any question, and we will cover these questions, I guess, at the end. Yeah, so I think that's it from me. Eric, the floor is yours.
Cool, thank you. All right, share my screen. And we will get rolling. Okay, so hopefully you could see my VS Code now. Yes, okay, good. Zoomed in a little bit further so we can see it well. So yeah, my name is Eric Sims, and I am excited to talk about network analysis in Python today. It is one of my favorite kind of hobby topics in data science. So a bit about me, and then I'll talk about what we're going to cover today, and then we'll jump right in. So I'm currently working as a senior analyst in strategy and analytics at LendingTree. I support the small business and investments verticals currently, which are both a ton of fun. Before that, I did my master's in analytics at North Carolina State University. And so if you're interested in a graduate program in data science, I'm definitely happy to talk about my experience. And I totally loved it. It was fantastic. As you can see here, I'm a LinkedIn junkie, and I'm there quite frequently. And so if you have questions about the things we covered today, you can find me there, send me a message, or of course in the Data Talks Slack as well. And so a couple of quick housekeeping notes. First, if you want to connect on LinkedIn, use the QR code here on the left. If you want to view the repo and the notebook that we're going to be going through like right now, then you can go ahead and you can visit this GitHub repo. My GitHub is Eric, github.com/Eric Postmaster, if that helps as well. And then you can follow along, or you can just, yank code and steal it for your own project later. That's totally fine. So the other thing I want to say is most of what I'm going to say in this webinar, because this is going to be fast, I have a lot of stuff scripted out. So you'll notice it's going to be written, a lot of it on the screen, because I know that not everybody listens to like my brand of English or American English accent all the time either. So I want to be like easy for anybody to understand and pick up and just roll with. So today we're going to talk about components of a network, nodes and edges. We're going to talk about 3 different ways to create a graph in Network X, which is the main Python library I use for network work. And then we're going to talk about capturing motion of information with directed and weighted graphs, and then how we measure importance with 3 different types of centrality. So let's get rolling. So networks are everywhere, whether you recognize it or not. You're part of networks every day. The roads we drive on, the phones we text on, the Data Talks Club Slack channel, all are networks. And it doesn't stop there. Your credit card, your passport numbers are part of a huge traceable network, so that, that's how we fight fraud, right? And then my favorite network, the blood pumping through my veins and my heart, the electrical signals zooming across the synapses in my brain, those are my favorite networks because they make me work. So a few professional applications of networks worth keeping in mind are fraud detection, corporate knowledge and information spread, route optimization, organizational charts, right? And so today we're going to cover 2 things. One is how to create and visualize a network, and we'll do that with a simple Lord of the Rings network. And then we'll talk about how to analyze a network, and we'll use some Star Wars data for that because, as you can see from my background, I'm a Star Wars nerd. So another word for network that maybe you've heard before is a graph. And so I'm going to probably use network most of the time, but if we switch back and forth between network and graph, they mean the same thing. So how do we actually make that network to analyze? We're going to look at those 3 different ways, but first we can talk about the components. There's nodes, and there are edges. So if you think of a social network like people who know one another, then the people are the nodes and the connections between them are called the edges, or sometimes called the links, right? And so here in this picture, you can see Eric, Shruti, Mark, we would be the nodes, and then my connections to those would mean that I know Mark or Mark knows me, and Shruti and I know each other, but Mark and Shruti don't know each other, right? And so today we're going to talk about 3 different ways to create that network. One is with what's called an edge list. The second is called an adjacency matrix. And then the third is using JSON, which is a non-tabular format if you're not familiar with it. So we'll use NetworkX to create, visualize, and analyze the networks, and we'll use NetworkX and Matplotlib, which they kind of work together nicely to make a basic network, which you can see here on the left, which is basic, maybe useful, kind of ugly. And then on the right, the after network, which looks nicer and conveys a little bit more information for the viewer. So let's get right into creating a network. So the first we're going to use is called an edge list. So that's a list of sources and targets that represent every connection in the network. And so we can import a few different packages, which you can see here, pandas you're familiar with. NetworkX is going to be our workhorse. This JSON graph is another NetworkX package that we're going to need here in just a minute when we work with JSON, obviously JSON, and then Matplotlib. Oops, I need to turn on my kernel. And then lastly, we'll import pickle just because it can be useful, but we're not going to use it today. But pickle can be useful because creating networks can be like layouts, can be very computationally intensive. And so if we use pickle, then we can compute that once, and then we don't have to compute it again. We can just load it. So anyway, for future reference, pickle's loaded. All right, so here you can see here in our data file, we have this lotr edgelist.csv. It's also in GitHub, so you should just be able to execute it and get your code. Now what we can see here, or your edge list, I mean. And what we can see here is in this list of sources, this is one connection, and this is the target that they are connected to. So you can see Bilbo is connected to Gandalf, Bilbo is connected to Frodo, but you can also see that there's some redundancy here. Frodo is connected to Bilbo, just like Bilbo is connected to Frodo. But in this edge list, redundancy doesn't matter. If it's there once, or if it's there twice, or if it's there twice and in reverse, it doesn't matter. We're only going to see one connection, and that's okay. We'll kind of get a little bit more into the direction of it as well as the weight in just a few minutes. So this is our edge list. The main thing that you need to know is that each of these names that are unique are going to end up being a node, and then the connection will be the edge, right? And Network X knows how to create the graph from that edge list and get both edges and nodes from it automatically, which is kind of nice. So first we have to create a graph object. So in Network X, graphs are usually called G, like in the documentation. So you'll see that a lot in the docs and in Stack Overflow. I usually like to use more descriptive graph names so that I know what I'm working on when I'm way down my notebook in work or something. But just for this first example, we'll stick with G to keep things consistent. So we're going to use this from pandas edge list function and tell it the source and then the target columns, which I already named, so that they'll be easy to find. But you could name them anything, like depending on what your graph is showing. It could be employee and coworker, or superhero and arch nemesis, whatever you're looking for to illustrate the relationship that you want to analyze. So we'll go ahead and do that. There we go. And then we're going to use this function nx.draw to take a first look at the network. So into nx.draw, which you can see down here, we will pass the network that we want to draw. And then we're going to use this, its position argument. Now the position is what's going to specify the layout, and then some information about what we want to see for the nodes. We want them to have a label. We'll give them a color, and we'll make them 3,000, the node size of 3,000, just so they're nice and big, easy for us to see. This layout thing, it used to be kind of confusing to me. So basically what it's saying is, I want you to draw this network, and now because networks need to be told how to be drawn. What algorithm should they use for the layout? There are lots of different layouts that you can use here, but basically you just pass a layout and then pass the network that you want to use into that as an argument. Circular layout is a good one. We'll look at another one later. That's my favorite. So when we run that, we'll see here we get this nice, it'll put all of our nodes in a circle and then connect them according to the edges in our edge list. So you can see here, Bilbo is connected to Frodo, Frodo's connected to Bilbo. It's just one edge. Same thing with Gandalf and Merry and Treebeard. And Treebeard is only connected to Merry, right? Nope, not connected to anybody else. So he's kind of hanging out there by himself. So that's how you make a network from an edge list. So now we're going to make the same network, but in a different format from an adjacency matrix, because you might be receiving, you might have data in different formats, right? So I want to make sure we're covering that. So another way to make a graph is with the adjacency matrix. And specifically, we'll do this one from a pandas adjacency matrix, but you can do it from a NumPy adjacency matrix as well. So the way that this looks is you have the, let me show it here. You have the node names here across the top, and then you also have them here on the left side as the index of this matrix. And then a 1 will show anywhere that they interact in some way. And just so you're aware, this code up here is just reading in the CSV and then just kind of reshaping it, putting the nodes as the top and as the left side, and then getting rid of the index column. So what we can see here is that anywhere there's a 1, that's the same as if there is an edge between two characters in our edge list, right? And so that means that Frodo interacted with Bilbo, Gandalf interacted with Bilbo, right? And then like we saw, Treebeard is all zeros, but he did interact with Merry. And so that's why there's a 1 there. So that's the most important thing, I think, to notice about the adjacency matrix is how to read that. Next is the diagonal is all zeros. And we know that it's all zeros because we already know that characters are kind of the same. They're in the same scenes as themselves or whatever in a movie. So it doesn't really add any value unless you wanted to talk about like Gollum and how he kind of has split personalities and you could make a self loop with that or something like that. But essentially that's what we're working on here is we'll just leave these as zeros on the diagonal. And then the last point is this matrix is symmetrical along the diagonal. And that's because our edges are undirected, right? It doesn't matter if Frodo and Bilbo interacted or if Bilbo and Frodo interacted. So you could essentially take it along the diagonal of zeros and fold it across itself, and you would have the same. So you'd have the same triangle of a matrix left. So we'll see the directional component of that in a minute, and then it will matter. So that's why for now we're good with having it be a symmetrical matrix. So if we draw, first we'll create the graph object, and then if we draw it, it should look pretty much the same. All right, there we go. For some reason, it changes the position of Frodo and Gandalf in this. It's probably just the way that I put it in the edge list originally versus the way it pops up in the adjacency matrix. But otherwise, this is the exact same graph. And then lastly, we'll talk about how to make it from JSON. So JSON's a non-tabular format. It might be different from a format that you've seen before. JSON is divided into 2 sections, nodes and links. And so let's execute this and I'll show you. So I'm actually going to open this in new tab here. So in JSON, it divides up the nodes and it puts them up here so you can see each of them. And then down here, it creates a links or edges section where you can see that the weight is equal to 1, and then it gives the source and the target. And this one, in this case, it's not redundant. It removes any of that redundancy that might have been there before, or it doesn't require it. So that is what JSON is going to look like. And then this is just a little helper function I made that will put the library, read the file, open the file, and then return it as a graph. And then, so we're just going to put that into this, G_JSON graph file here, graph object. And then lastly, we will just execute that and we'll see, again, same thing. So we have the same data, but you can bring it in with three different ways of doing so. And there are more ways that you can find on Network X, but I think these are probably going to be the most common things that you'll run into. I specifically included the JSON because in the Star Wars data set that we're going to look at in a minute, there are multiple Star Wars episode data sets, and they are all in JSON. And so if you're interested in doing a follow-up project or any follow-up analysis with this, you want to use the JSON stuff. Okay, so also, speaking of that, with that, if you want to do products or projects following up, Twitter and Reddit are also great places to get network data for projects and wrangling practice. I like Reddit a lot because it's like you can look at like a specific subreddit and then a specific post and then get information about the specific people who are posting and replying and commenting, things like that. It's cool. All right, so let's talk about what we can learn from a network. Now, this is where we're going to now make things, instead of just having edges between everything, we'll make them a little bit more interesting. So we can see and track some motion using a directed graph. So previously, we only saw undirected graphs when you have a line connecting two nodes. But if you want to show the flow of something like money, like what if Bilbo gave Frodo some money, but Frodo didn't give any money back, then we could represent that with an arrow to show the direction. And when we show the directed flow of material, information, or some other transitive relationship, we call it a directed graph. So here is an updated edge list, which this data is also in the repo. So this is an updated edge list showing who gave money to whom in our Lord of the Rings group. And you'll see now it's actually much shorter. Now we've only got eight different lines. And this matters now because before Bilbo gave to Frodo and Frodo was connected to Bilbo, but not anymore, right? And so now the order of the source and the target is actually important. And so here it is again, we can see in an adjacency matrix. And now you'll see that our matrix is not symmetrical anymore. So Bilbo gives to Frodo, but Frodo does not give to Bilbo. Now it's a 0. And so not having that symmetry is important because now we can see directionally what might be going on. And so we can do the same, we can create this directed graph object the same way that we created the undirected object, but we're going to do one extra little thing, and that is adding this tiny little parameter create using the nx.digraph for directional graph. And then when we do that and we plot it, we'll see here that we have arrows going from whoever to whoever they were giving. And so we can see that Bilbo and Gandalf tend to give more than they receive. And it looks like Frodo is a freeloader because he didn't give to anybody, but he did receive from 3 people. So Frodo. So we can't tell who he mooches off the most, though. In order to see that, we would need weight, because it could be that Gandalf gives him a bunch more money and Merry just gives him like $1, right? And so we want to be able to see the weight of those arrows so that we can understand that relationship a little bit better. So down here, we have the same adjacency matrix, but instead of ones, now where we had ones, now we have numbers. And so we can see that the relationship, so here's the column of everybody that gives to Frodo. And we can see that Bilbo and Merry each give one, let's just say $1, whatever kind of money they use in Lord of the Rings, to Frodo, but Gandalf gives 4. And so we can see he has a much much more lucrative. Frodo has a much more lucrative relationship with Gandalf, I guess. And so here we'll just create this same graph object that we made before, but just with the directional graph and then the weighted matrix. And then we can, if we want to, see the weight of each edge. So this is showing us just a different format. And then we plot it. Let's see, is there anything really? Yeah, so important stuff we need to see here. This one's a little different. So in this one, because we're plotting it this way, we can see now Gandalf has a much heavier arrow, whereas everybody else giving to Frodo has a very thin arrow conveying motion, right? So to help kind of walk through this code just a little bit, we can see that First, we use this draw network X nodes, draw networks X nodes, and that's going to specifically draw the nodes and only the nodes. If you passed that, you would just have blue dots in a circle on your page. And so you're going to give it the same information though that we already gave it. Tell it the layout that you want it to use, and then what colors and stuff you want. And then we use the draw network X labels to actually put the names of the nodes onto the nodes. Make sure you pass it the same layout, because if you don't pass it the same layout, they won't be aligned, right? So that's how we know where to drop everything. And then the weighted edges. And so with the weighted edges, we're going to use this is the graph object, this G underscore WT dot edges, which is just going to show us the edge information. And then we're specifically going to ask for the weight attribute. So if we come back up here, we can see that there's an edge from Bilbo to Frodo with a weight of 1. And so what it's doing is it's going to say for each edge, grab the weight and then draw that edge where we want it to be. And so when it came to Bilbo, it says, oh, there's a Bilbo Frodo edge. What's the weight? It's 1. Okay, draw an arrow with weight 1 between Bilbo and Frodo. And now go back and do it again. And so it would do the same thing for every node and edge, or for every edge in the network. Hopefully that kind of helps a little bit. And then if you are stuck on the edge thickness, I just included this link to Stack Overflow because I was stuck on the edge thickness. This was really helpful. So definitely feel free to check that out. So that's how we can see, we can take what would be otherwise a pretty bland and uninformative network potentially, and we can turn it into something that shows the flow of information or value of some sort, and maybe kind of give us a little bit of a sense of importance of things. And so, but if we want, we can understand more than just the connection, direction, and weight of any one node, but we can understand how information might flow across the whole network, right? And so that's called centrality, because it's one thing to know if, say, a person is very wealthy, but how do you capture if they are influential, right? Because you could have a person who is wealthy but keeps to themselves, or you could have a person who's wealthy but really like they spread their influence, whether that's through by spreading money, or if they just know powerful people and they use that wealth to influence policy or something like that, right? And so the way that we would do that is by using a concept called centrality, right? So if we can see that, we can see weight and we can see direction in a normal data frame, you know. But the cool thing about networks is we can see how things work from multiple hops away. And so one way to think of that is like in terms of traffic. And I like to think of it. So I happened to be, when I was prepping this, I happened to be online during the time that rush hour is happening in Hong Kong. And so I grabbed just this screenshot of Google Maps where we can see each of these roads can represent an edge in Hong Kong's street network, right? And so which of these edges would you say is the most important? Like you can have, say, this edge out here where there's not a lot of traffic. And so I would say this edge is probably not, at least at the moment, as critical as another edge, like this one right here that's dark and then getting darker with traffic going across the causeway here, right? And so if there was, let's say, a stampede of elephants on the middle of this causeway and they had to close it down and send traffic somewhere else, all of these people would have to drive way around in order to get to central Hong Kong while the elephants were being cleared out, right? And so that shows you if all of these people, thousands and thousands of people, had to take a much longer route to get from point A to point B, then that tells you that that edge is very, very important. It has high centrality, right? So anytime that you are stuck because there's an accident or a traffic jam or a stampede of elephants on the freeway where you drive and everyone's rerouted, that's a perfect example of centrality. On the flip side of that, if you woke up tomorrow and the street that you grew up on was closed, would traffic be backed up for miles? Would it affect anybody? You know, I lived on a, you know, small neighborhood or whatever. So for me, it would probably be like a few dozen people would be a little bit inconvenienced, but that's about it. That road has very low centrality. It wouldn't really affect anybody else in the network, right? So centrality is a super important characteristic of different nodes and edges in a network. So we're going to look at that now with Star Wars. So the first we're going to look at Star Wars Episode 4, and it, like I said, it's in a JSON format. There is also this data set here on Kaggle, so it's linked here in the notebook that you can go if you want to see episodes 1 through 7, or even like a whole network of all of the different nodes connected across all the episodes. So we'll just go ahead and read that in and then create the Star Wars graph object. And now we will draw it using my favorite. It's the Kamada Kawaii layout. It's my favorite. It just looks so cool. They always look cool. Okay, so we can see that we have a network here that has a kind of an interesting shape, but the labels really aren't very useful to us. And so we can look at the node data to figure out how we could improve that. So this is an important part. Like, this is just like drawing back to the basics of anything data related, and that is you have to do some exploratory data analysis and make sure that things actually make sense. Because I don't know why whoever made this network made these nodes numbered. It's pointless actually, because if you see the node names are 0 through 21, but using data equals true in these nodes, you can see that there is some more information underneath each of them. So you can see that each node has a name. The name in this case is R2D2, has a value and a color associated with it. I don't know what the value and colors mean in this one, so we're going to ignore them, but we're going to use the name to label our nodes. So what we can do down here is we can say get node attributes from this network, and I just want the attribute called name. And we're going to put that in this labels. I think the output is a dictionary in the labels dictionary, and then we'll output that here by drawing the network. When we draw the network, it's the same thing as we've been doing before. We're going to draw the network. We're going to use the same layout, label or node color with labels. Everything's the same, except we are going to say labels equals labels, because we don't just want to pass the default labels, which is just the first key in the network. Instead, we're going to pass something specific to it. And then just to make it look a little nicer, I changed the edge color and the edge width of the network. Okay, so now we can see, now we're starting to get somewhere. Like, it's still ugly. It's not really the prettiest graph, but we can at least work with it. There might be some characters here that we recognize. Like, we can see Luke, we can see C3PO and Leia, and Han's kind of buried under there, but he's there. So now, because we can start to get a feel for what this network looks like, we can work with it. Let's get some centrality metrics to see who's the most important in the network. Now, you can probably guess some of the most important people, because if you've seen the movie, you know that there are a few people who are more important than other people in the movie, but that actually kind of makes it really helpful because you could see things really clearly here. Okay, so the first kind of centrality that we're going to look at is, I think, the most intuitive. It's called degree centrality, and it's basically saying of all the nodes in the network, how many, like what percentage of them are connected to this one, or your degree is basically like the number of connections that you have, right? And so if you're on Facebook and you have 500 friends, your degree is 500, right? You don't have 500 friends in real life, but maybe it feels good to say that on Facebook. So if you have a high degree centrality, then it means you have a lot of nodes directly connected to you. And since we were talking about direction, I'll throw out, there is also in degree and out degree in case you're in a directed network, but we're not going to worry about that in this case. So it looks like I need to re-execute that, and I'm just going to hide that. Okay, so this is a quick basic example where you can see that node 1 here would have a high degree centrality because all the other nodes in the network are connected to it. Whereas node 2 is only connected to one other node in the whole network. So it would have a low degree centrality. So next we're just gonna, I made this little, again, helper function, because when you print the degree centrality for everybody, it's printing from a dictionary. And so since that's not ordered, it's just going to print the whole dictionary. And so if you only have, 10 or 15 nodes, it's no big deal. But if you have like 300 nodes, it's a little bit unruly. So basically what this helper function is going to do, I left a nice doc string here for you. So if you have questions, come back to it. But basically what it's going to do is you can say, I want you to take a dictionary. I want you to grab the top 10 and show them to me. Or you can say, I want you to take this dictionary. I want you to use a value cutoff method, and anybody who has a degree above whatever value cutoff, then you can use that instead, and it will show you the nodes that you want to look at. So we'll take advantage of that. Whoops, down here. So the first thing we're going to do is we're going to look at the top 10 nodes of the Star Wars network and their degree. And then we're also going to look at it by their degree centrality, just to kind of help make the connection of those two. So here we can see that node 3 has a degree of 15, node 7 has a degree of 12, which translates into a degree centrality of 0.71, or that means that node 3 is connected to 71.43% of the other nodes in the network. So hopefully that helps kind of understand what the degree centrality actually even means. So it's hard to tell which node corresponds to each character, like I said earlier. So what we're going to do is we're going to rename the nodes so that we can just get rid of the number that's really not that helpful. And we're just going to use the name attribute from earlier. So the first thing you'll see here is we're going to create a node names dictionary here. And then we're going to pass the name from each node into this node names, and then just use this networkx relabel nodes function. So clearly this is a thing that has to happen often enough that it needs its own function. So you can relabel the nodes in the Star Wars network with the node names object that we just created a second ago. So we'll go ahead and we'll do that. And now we'll print out the exact same thing that we were just looking at. And now we can see that Luke has a high, Luke Skywalker has a high degree centrality. Leia has the next degree centrality, followed by C-3PO, R2-D2, and then the other characters. Now, there's something that might surprise you about the degree centrality. It kind of surprised me, and that is that Darth Vader did not even make it into the top 10. There are other types of centrality that might help us see why he is an important character, and surely in other movies he would become an important character. I think, just as a side note, I think that just shows that like why Star Wars is pretty cool, because Darth Vader like doesn't even interact with the main character. Well, if you think of Luke Skywalker as the main character, he doesn't even directly interact with him in the first movie, and yet he was like such an impactful character. So that's pretty cool. Anyway, we can look at, if we want to now look at this visually, we can look at these high degree nodes by assigning them a specific color in the graph. And so this is actually a trick that I learned from Keith McNulty. He's writing a book about organizational network analysis. And this is it's a cool and easy way to assign colors to things. So the first thing we're going to do is create a list of our top nodes. And so that's just the same filter dictionary thing that we just did a minute ago to get the centrality for everybody. But we are just going to use the top 10 and then put it in a list and create that as the high degree nodes object. And then now we're going to say in a list comprehension, if I is in this high degree nodes, then give it a color of C1, which in Matplotlib is just orange. And then otherwise, give it the color C0. And that's for all of the nodes in the network. And so we should have, by the end of this, we should have blue and orange nodes. And then let's see here, just to make sure that did what we think it did. Did it not do what we think it did? There we go. Okay, so yeah, in colors, we can see we have here, I'm gonna open it up. So if we look at the colors list that we just made, I don't know why this is being so slow. It's not a very long list. There we go. We can see that we have just a list of those different colors that are going to be passed in a specific order to each of the nodes, right? So we have these C1, which are going to be the orange ones, and then these C0, which are going to be blue. So we have that list. And then down here, we're going to do the exact same drawing that we made before, where we have the Star Wars list, or Star Wars object, sorry, the positioning and the layout that we like, the node size that we want, except the only thing that's different is here with node color, we're going to pass colors so that it will connect them, color them the way that we want them to. And so here we can see, not surprisingly, because this is a small network, the best connected individuals are often connected with one another, right? We don't have like a little island hanging out up here with like just like a really well-connected community, side community or something like that. That'd be kind of weird. It wouldn't really fit into a single movie, right? Maybe across multiple movies you could have that, but in this particular network, individuals are connected with each other. Also, we only took the top 10, or we took the top 10, which is like 50% of the network. If we took the top 5, we'd see a deeper core of the network. And I was thinking about that while I was prepping this, and I decided to take a look at it. And so I threw in this little bonus section, and that is we can look at a deeper core of the network, not just taking the top 5 by degree, but actually a deeper core using a function called KCore. And that allows you to specify a degree that you want to see and then only show nodes with at least that degree. And I found something cool in this network using a KCore of 6. So the way that works is I just use this nx.kcore, and then I pass in the graph object and then whatever K level you want. And you can try it, like using a KCore of 2 is a good way to just kind of like clean up the edges of like little fuzzies that only have one connection, so you can kind of clean things up a little. But as you want to get to a deeper network, we can see here that now we just pass in this KCore object, which is kind of the pared down version of the network. And when we do that, we get a fully dense network, because it just so happens that the 1, 2, 3, 4, 5, 6, 7 characters who have the 7 core characters of the movie all have 6 connections to each other. And so they all have, they will all show in this particular graph. So anyway, I thought that was pretty kind of interesting, kind of surprising. I wasn't expecting it. Usually when you get, and for me at least, when I get up towards past 5 or so, usually you get like 1 or 2 nodes, and you don't really get very many. There aren't very many that have such strong connections, at least in the graphs that I've been working with, which are generally smaller. Okay, so that's degree centrality. Now let's look at betweenness centrality. So betweenness centrality is a lot like that Hong Kong road example that I was using just a minute ago. So it's a way of saying how many of the shortest paths from A to B, whichever A to B's it might be, whether that's from Luke to Darth Vader or from Han Solo to, Leia or R2D2, whatever, it doesn't matter. The shortest paths, how many of the shortest paths go through that specific node or edge? So in the specific example of that road being closed, that's a really important road, and many people use it for their optimal drive home. And so that road would have a high betweenness. In this case, we're going to look at node centrality, but you can also look at edge centrality in the case of roads. In the case of node centrality, we can look at, I'm just going to look at the top 5 to keep it simple. And we can see that Luke, Leia, and Han have a much higher betweenness centrality than anyone else. And we can kind of see why if we look at it visually. So what we're going to do is we're going to assign that same colors thing, but we're going to assign the color if it's based on those 3 people. And then this is just to add the labels to the plot and everything else we've already seen. And so when we plot that, we can see why they have such a high betweenness. And that is because Han, he is the only way you can get out to these other two nodes. And Leia is one of only 2 ways to get out to these other 3 nodes, which happen to be like the Imperial, like Darth Vader and Grand Moff Tarkin, right? And so they are both connected to people that otherwise you can't get to. Same with Luke. Luke is very connected to over here. When we put labels on it, you can see that it's like all the rebels that fly their X-wings and things like that. And so because these people are connected, they have kind of some unique connections, they bring some unique value to the table. Let's say that you were somewhere in here and you were really trying to, network your way into the empire and try and get lunch with Darth Vader. I don't really know if he eats lunch, but I suppose maybe he does. Leia would be a great person to talk to because she could make a good intro for you. It might be a strained introduction, but that's the idea here. Is you can see who would be a potentially good relationship that you could leverage or build in order to network into wherever you wanted to go. I would suggest not networking into there. It doesn't end well. Spoiler. So lastly, we can combine these metrics into a single visualization and we'll show different levels of importance. So we'll make the nodes with the highest degree larger than the rest. So we'll use size to convey degree. And then with the highest betweenness, we'll turn into a different color because it's nice to see this, but it only tells us one thing. It's only one small part of the picture, right? Sometimes if you have high betweenness but low degree or the other way around or something, then you want to, it really helps to be able to see both kinds of metrics at the same time. So what we're doing here is we're doing that same thing with the node size with the list comprehension here. And we're just assigning a size of 300 to the high degree nodes and 100 for the other nodes that have a lower degree. Then we're assigning these same colors like we just did a minute ago, same labels. This is all just copy paste all the way down. And then adding the labels here and the colors here, and then the node size here. No sweat. And so now we can see that the ones that have a high degree, they're these chubbier nodes here in the middle, they aren't necessarily the ones that all have a high betweenness as well. And so this is like again, coming back to networking, you may see somebody who has, 10,000 followers on LinkedIn, like this person here. But maybe somebody who also has 10,000 followers on LinkedIn can get you into a network that this person is not necessarily as closely or as uniquely connected to. So networks are useful because you can see value that you wouldn't necessarily be able to see just by looking at data in a data frame because it shows some different relationships. So I think that's pretty cool. And then the last centrality that I want to look at here real quick is closeness centrality. Now we're going to leave Star Wars in a galaxy far, far away and talk about how rumors spread, which is super interesting, right? Or how influencers can be influential or look influential, but not really be influential. Right? So if degree centrality counts the number of people who are very close to you, like directly, then you could say that closeness centrality tells you how close you are to everyone else, like not just the people who are directly connected to you, but the people who are directly connected to the people you are directly connected to, right? So your second degree connections or third degree. So even if you aren't connected to a lot of people, you can have high closeness if you're connected to a few people who are connected to a lot of people. So a good example of that would be like, let's say, I don't have that many. Okay, I'm not on Twitter, but if I was, I wouldn't have very many connections on Twitter, right? But if I didn't have very many connections, but or followers, but if one of my followers on Twitter happened to be like the president of the United States or the president of a country or something that has potentially thousands and thousands or even millions of followers, and they retweeted me, then my closeness to the network just got huge, even though I only have 10 followers, right? So in this last example, we're going to talk about how to spread news or a rumor. It might help you figure out who you'd want to talk to in order to do that. You could also think of it in terms of influencer marketing. So let's say you're a marketer, you have a limited budget, and you want to get the word out about your product and make the most of it. So here's an example of effective gossip or ineffective gossip. Okay, so we have this gossip effective CSV file that we will put into using a pandas edge list. We'll put into a network graph object, and then we're going to put colors on the main influencers in this network, and then we'll draw it. So here, one is going to be you, the marketer, right? And then these light blue nodes are the influencers. So you can see I only have to talk to 5 people, but then like 50 people end up hearing about it because these 5 people, I picked the right people to talk to. So now, because I or you or whoever is this one, you have a high closeness centrality, even though your degree centrality is not that high compared to these influential, these influencers here, right? Now, if there's a marketer that doesn't do their homework and they spend money on influencers kind of just shotgun style, just like throw it out the window, then you end up with an ineffective graph, which we can see here, where in this case, they talked directly to one influencer and got the word out, but then they talked to 4 people who were only connected to the influencer, right? And so it takes an extra hop to get that information out. And you can think of every extra hop is risk, right? Because there's a decent chance that node number 6 here is going to forget, or is going to be too busy, or is going to have a better offer come along and isn't going to pass along the word to number 5, which would effectively wipe out like 20% of the market or network, or people you want to gossip to about things, like whatever it is, right? So that's why closeness centrality is really interesting, because it's talking about how long would it take for you to say something and have everybody else hear about it, right? Or any one node to hear about it. So we can quantify that by looking at the closeness of node 1 in the effective and ineffective gossip. So in the effective gossip, the average shortest path length is 3.37 hops, right? And then in the ineffective gossip, the average shortest path length is 4.39. So it's basically another person worth of hop. And you can see that the closeness is, about 20% lower, roughly, through ineffective gossip. And so you can reduce your friction of information flow by 25% just by communicating smartly, if you will. So that's a few things about networks I think are pretty cool. To kind of wrap up where we've been, and then Alexi, if you got any questions or anything, we can talk through it. Talked about nodes and edges being the components of the network. 3 ways to create a graph using an edge list, adjacency matrix, or a JSON file, all of which would be, I think, very probable to run into at any time. Capturing motion with directed and weighted graphs, which I think is really cool. And then measuring the centrality with degree, betweenness, and closeness centrality. And there are a bunch of other kinds of centrality that you can use. Like there's eigenvector centrality, which is a cool way of looking at like who is, if you're connected to important people and stuff like that, and other things like that. And then other topics that you might be interested in, or where I would like to go in developing further stuff, is talking about bridges and brokers. So bridges are those critical areas that there's literally only one path from this part of the network to this part of the network, or maybe there's one person in the middle of it. We really want to know who those people are, because if it's in your organization and that one person is the only person that knows how a system works, you need to find that person and you need to make sure that there's some redundancy there. Otherwise you could be in a world of hurt if that person gets a really great job elsewhere or wins the lottery or something like that. Community detection is really cool. You can use the Louvain algorithm or others to find sub communities within Star Wars or within other networks. I did it with the Star Wars network, just didn't have time to throw it in here. Pickling complex graph layouts for later use, like I mentioned. And then lastly is interactive visualizations, where you can use something like PyVis in Python and use Java. It uses JavaScript to be able to actually like zoom in and move things around and see different relationships. Or Gephi, which is a no-code platform for network use. I think it's on Java. But anyway, it just uses a graphic user interface. So it's pretty user-friendly and allows you to do a lot of stuff pretty fast. So anyway, that is some cool stuff that for further investigation. And yeah, hope that was useful, a helpful introduction.
Yeah, it was. Thanks a lot. So there's a comment from Lila she's saying that this is much cleaner than the tutorials I found. Very helpful. And I agree
Yes.
that.
I'm so glad to hear that, because I felt the same way.
Yeah, and this is well, for me, I have watched Star Wars many times, so the examples were like something I could relate to. And then the example with Hong Kong, even though I haven't never been there, like I could relate because I lived in a city where there was a bridge and when the moment a car accident happens on a bridge, then basically there is a transportational collapse.
Yeah,
So
absolutely. We've all been in traffic. We've all been in
yeah,
traffic, I should say.
yeah. So we have a couple of questions. So one question from Sebastian is: are there advantages of using JSON versus GraphML network format? I don't know if you know about GraphML. I
I've
assume
heard
this
of
is.
GraphML, but I don't actually really know for sure.
Mhm. And this JSON format, this is something that NetworkX uses? Or like this is when you save like a graph, this is the format it uses, or what is that?
Just the JSON format, you
Yeah,
mean?
exactly. I think it has a specific like structure.
Yeah,
That,
yeah. So it doesn't JSON is I should say I'm trying to see which one I should answer first. So Network X uses dictionaries.
Mhm.
They say dictionaries all the way down. So it looks similar. I guess you could kind of say because it does keep your nodes and your edges separate.
Mhm.
And so you can export from Network X. You can export to whatever format you want, including JSON, or I think you can export to GML and like GEF or GEFX, and so there are a whole bunch of different formats. It just depends on. I just went with what I thought has been in my experience the most common to run into to need to ingest, but you can also export. You can import and export in several different formats.
Yeah. Thanks. You mentioned a couple of useful, nice data sets to play with. You mentioned Reddit, you mentioned Twitter. Is there anything else that you would recommend for people who got really excited about this webinar? Maybe they want to try something
Oh yeah,
like a
for
bigger
sure.
graph, perhaps, than Star
Yeah,
Wars. Do you have some
yeah, for
recommendations?
sure. Let me see here. I was actually going to include a big old network in this, but I just didn't end up having time. Let me grab a link here. So through Stanford has, maybe I can, I'm going to drop this in the chat, Alexi, just for you. You can post it wherever you want, but maybe I'll also change my screen share here and I'll show you. New share. Here we go. Okay, so you should be able to see the snap page. Yes, cool. So this is the Stanford Large Network Dataset collection, and they've got a bunch of them. So there's like Facebook and Twitter and all these different, Wikipedia, Bitcoin. These are social networks, but then they've also got networks with ground truth communities, citation networks, collaboration networks. I'm looking at an Amazon network right now. So if you want to look at, and this is in this case directed networks, undirected networks. So yeah, like go crazy on this page. I actually just found this fairly recently. And there are others that you can find as well, but personally, like this is my new favorite site to go and find networks, because otherwise things that you can find on Kaggle are generally small because sometimes they're like handmade even. And so that's a labor of love that can be a bit tedious. So I would highly recommend using this. The other thing that's cool about the Snap data is it comes up in a lot of publications. And so you'll see like the California roads data is in a publication. So it's nice to be able to go back, find the data, use it yourself, work with it. Actually, if you're interested in the GitHub repo, I think it's still there. Maybe I moved it. There might still be a pickle file of the California network in the Kamada Kawai layout, because I just turned it on and left it running because it just had so many nodes. I just had to let it calculate for a couple of hours while I went to bed actually. So yeah, I would highly recommend this page.
While we are talking about this, your repo, maybe you can share a link, because there is a question how to access this.
Yeah, for sure.
So I assume everything we talked about, everything you showed was in this QR code that you showed at the beginning, right?
Yes. Yep. Everything's there. So basically, it's just this webinar content, Jupyter Notebook. You can't miss it. It's literally the only thing that has code in this whole repo. So it should be easy enough to find.
Okay. I have just put it to the live chat. Okay.
Sweet.
And do you have any recommendations like for follow-up for people who want to follow up, like books or cool articles or cool courses, perhaps, to get more into network analysis?
So there are a couple of network analysis courses on Udemy. One of them, let's see here. I took one and I'm currently enrolled in the other because it gets into like it briefly touches on NLP with network analysis, which I think is really cool. My number one recommendation would be to follow David Knickerbocker on LinkedIn and his hashtag 100 days of networks because he's awesome. He just finished it, but he's posted like every day all the progress that he's made, and it's super super interesting, and he has a lot of book recommendations and stuff like that. But otherwise, I would say those Udemy courses are cool as well.
So I'll make sure to include all these links in the description. And yeah, after we finish, please send me the links and I'll put them. Okay, sure. I don't see other questions open up. Let me check. Yeah, there are no other questions. Yeah, I guess, I don't know, do you have any last words?
Oh, that sounds scary. Nope, I think I'm good.
Last words before we finish the webinar.
Oh, okay. I guess the last thing I would say is if you if you decide to do something with it, like one, be patient with the Network X documentation because it can be a little bit hard to understand and it's a little bit lean. It'd be nice if it was maybe a little bit more fleshed out. If you get stuck on something or if you're working on something and you think it's interesting or you're stuck, like send me a message. I don't know that I can necessarily fix it, but I'm more than happy to talk through it. I think it's a lot of fun. And I've appreciated help that I've gotten on projects. And so I'm more than happy to help other people. So yeah, definitely connect in Slack or on LinkedIn.
No, okay, thanks. So the best way to find you is, I guess you mentioned at the beginning, LinkedIn, then Datadog Club, Slack, something else?
That's the best way.
Okay. Yeah, and then there is, for those who joined a bit late, if you go at the beginning of this video, there are two QR codes. So one is with Eric's LinkedIn profile and the second one with the code, right? And then there are cute dinosaurs in the middle.
They're adorable.
Okay. Yeah, thanks a lot for joining us today and for sharing your experience with NetworkX with us. And thanks everyone else for joining and asking questions.
Thanks a bunch.
Yeah, well.